Good morning, this is Dr. Jingbo Louise Liu. Today we start chapter 6, the thermochemistry related to the energy flow and chemical change. We are going to cover 5 key topics in this chapter. First one, the form of the energy and their interconversion. The second one about enthalpy during the chemical changes, particularly at constant pressure, and then calorimetry to measure the heat transferred during a chemical or physical change. And then we show you the stoichiometry about the thermochemical equations. The last key point will be the Hess's law. We are going to learn how to find the delta H of any unknown reaction based on the known reactions. The last topic is related to the standard enthalpies of reaction. We are not going to further discuss them, but you need to know the delta H naught for your reaction. So it's the known value. You can calculate them from the delta H for the formation reactions. So first of all, let's clear off several important terminologies about the transfer and the interconversion of energy. So first of all, we need to know the thermodynamics. Thermodynamics is a study of the energy and its transformations of the matter during either physical or chemical changes, also involved in phase transition. Thermochemistry is a branch of thermodynamics. Thermochemistry is dealing with the heat involved in chemical and physical change for that particularly interested matter. When the energy is transferred from one object to another, the energy can occur as heat and work. Energy appears as work and heat during the transfer. There's another two important terminologies called system and its surrounding. The system is a group of interacting or interrelated entities that form a unified whole, so you call it system. The meaningful study of any transfer of energy requires that we first clear off the definition of system and surrounding. System and surrounding, they are equal to the universe. The universe is the sum of your system and the surrounding. In the next slide, I will show you the system and the surrounding one more time by an example. There is one more called internal energy, one more terminology called internal energy E. The internal energy E of a system is the sum of the potential and kinetic energy of the particles present. The total energy of the universe remains a constant value. The change in the energy of system must be accompanied by the equal or opposite change in the energy of your surrounding. Meaning, the energy change of the system is the same as the energy change of your surrounding, but have opposite sign. If your energy gains heat, or if your system gains heat, your surrounding must release heat. Also, we are going to show you several examples. So in this slide, you see a beaker, you see a Erlenmeyer flask, you see orange-colored solution, you see a Bunsen burner, and some other devices. So the system, to repeat, is the group of interacting or interrelated entities that form a unified whole. In this case, your system is what you are going to study. So in this case is your reaction Erlenmeyer flask and the aqueous solutions in this Erlenmeyer flask. Anything else surround this system, you call the surrounding. The surrounding compresses everything else. So including this beaker, this volumetric, volumetric flask, and the pH meters, and Bunsen burner, etc., etc. Again, the system in this case is the contents of the reaction flask, anything inside of this flask. So the system and your surrounding together composed of your universe. And then let's see some examples. For example, so if you have this energy diagram, so which can show you the transfer of internal energy between the system and its surroundings. So if you have the figure A, for example, figure A showed the system energy decreases. Initially, your system have higher internal energy. After the consumption, the energy decreases during the final state. Therefore, your energy is released from your system to the surrounding. Energy released to your surrounding. This delta E for your system is smaller than 0. Delta E equals E final minus E initial. Figure B. Energy of your system increases. So if you have your initial state, that initial energy is lower, final energy is higher. So the delta E again equals E final minus E initial. This delta E is bigger than 0, meaning your energy is going to be absorbed by your system from the surrounding. The last one actually have A and B as well. Essentially showed you the similar ideas about the energy transferred as a heat particularly. And then we also want to mention one more time your delta E, the energy change, internal energy change equals the E final minus E initial. If you have a chemical reaction, delta E equals the E products minus E reactants. That's how you are going to determine the energy changes. Also, I have a figure 4A, figure 6.4A and 6.4B. Both again showed you the energy is transferred as the form of heat. For example, if you have this system, in your system, so you are going to have some gases and some substances such as your zinc reacted with hydrochloric acid, produce hydrogen gases and the zinc chloride. In this case, you generated the gas. This gas is going to do the work to the surrounding. So again, this case, the internal energy change released as a form of work. We need to know the sign conventions of your heat, of your work, of your internal energy change, delta E. Delta E can be calculated by the Q plus W. Your Q, which is the heat, plus your W, work, equals to the internal energy change. So this Q and W, they have different signs, meaning if you have the plus sign for Q, the system gains heat. Positive is plus sign, meaning your system gains heat. Similarly, if you have your W, which is positive, meaning the work has been done onto the system. On the other hand, if you have negative sign meaning the system releases heat to the surrounding, loses heat. Therefore, you have a couple different possibilities. If both Q and W, they are positive, meaning gain heats, and the work has been done to your system, in this case, your internal energy will be positive, will be increased. On the other hand, if your system releases heat and your system has been done the work, so the internal energy will be negative, will be smaller at the final state. If you have positive Q, negative W, so your system gains heat and your system also does the work. In this case, your internal energy is going to be depending on the size of the Q and the W. On the other hand, if your Q is negative, your W is positive. So the internal energy change, the sign for the change will be also depending on the size, on the quantity of your Q and the W. Another important law is called the law of energy conservation. So you already learned it. It's also called the first law of thermodynamics. The law of energy conservation is also called the first law of thermodynamics. The first law of thermodynamics states the total energy of the universe is constant. Make sure the total energy of the universe is a constant value. The energy of the universe is conserved. The energy of the universe is neither created nor destroyed. The energy of the universe can be transferred in the form of heat and work, or either in the form of heat or work. The delta E for your universe, the energy change of your universe, equals to the energy change for your system plus the energy change for your surrounding. This value is 0. The delta E for your universe is 0. Couple minutes ago, we mentioned the system energy change and the surrounding energy change numerically are the same but have the opposite sign. They cancelled out. Your energy have different units. The SI unit, the international standard unit of your energy, is in joules. This is J, capital J, meaning joules. The joules is defined as 1 kilograms multiplied by 1 meter squared divided by 1 second squared. We also know the calorie. The calorie was once defined as the quantity of energy needed in order to raise your temperature of 1 grams of water by 1 Celsius. So that energy required is called calorie. 1 cal equals 4.184 joules. I also suggest try to remember this conversion number, 4.184 joules. There is another commonly used unit called BTU, British Thermal Unit. The British Thermal Unit is often used to read the appliances. 1 BTU equals to 1055 joules. And then we are going to further discussing the sample problems. So your sample problems about the internal energy determination. I will give a 5 minutes break and then we come back to continue your chapter 6, part A. Thank you so much. You have a good day.